second part of the problem-solving section of Chapter 9. We begin where we left off, and that is at question 5, which states, an 1,800 kilogram car, let's call it object 1, okay, of mass 1, is stopped at a traffic light, but ends up being rear-ended by a second car, let's call it car number 2, of 900 kilograms, moving at a velocity of 20 meters per second, and let's say in the positive I-hat direction, since we want to work with the vector nature of velocity. The two then become entangled and move along the same path that M2 was originally moving in. In other words, they both move along the positive I-hat direction. We are asked to determine the velocity of the cars that have become entangled following the collision. Now, it is important here to note that this collision does not conserve energy, but rather only momentum. And so this is what we call an inelastic collision. And more importantly, since the car becomes entangled, it's a perfectly inelastic collision where, for example, V1 final equals V2 final, which we will call simply as V final. They move along the same direction, they are entangled, and so the masses following the collision are the combined masses M1 plus M2. Well, since we can only use conservation of momentum, we have to consider the momentum of the first object, car 1, prior to the collision, so initial, plus the momentum of the second object, car number 2, prior to the collision, and then consider that after the collision, the entanglement, M1 plus M2, causes them to move at a common final velocity. Now, they tell us that car number 1 was stopped at the traffic light, so in fact, car number 1 did not have an initial velocity. Well, here you can see very easily that we are solving for V final, which will be equal to V final as a vector, M2 times V2 initial divided by M1 plus M2. And when we plug in our numbers, see M2 is 1,800 kilograms times V2 initial, which is 20 meters per second in the I-hat direction. And that is divided by 27,000 kilograms, which is the, 2,700 kilograms, I should say, which is the combined masses. And so let's write this down here. M2 is 900 kilograms, isn't it? So let's make sure we get this straight. M2 is 900 kilograms. V2 initial is 20 meters per second in the I-hat. This gives us, and M1 plus M2 is 2,700 kilograms. And if we plug this into our calculators real quick, which I am going to do right now, since I'm afraid that I may have the wrong numbers, 18,000 kilograms meters per second in the I-hat divided by 2,700 kilograms. The kilograms, of course, cancel. That gives us 6.67 meters per second in the I-hat direction. So when the cars become entangled, they will move at the common velocity, their bumpers lock, for in other words, at 6.67 meters per second. Okay, next question. This question is the ballistic pendulum. Now, in the ballistic pendulum, we have to consider our old friend conservation of energy as well as our new friend conservation of momentum. So let's see exactly what happens. A ballistic pendulum is often used to measure the speed of a projectile, such as a bullet. A bullet of m1 is fired with an initial velocity, v1 initial A, and collides with a large block of wood, m2, which is stationary yet suspended from a ceiling and so therefore able to swing as a result of motion. When the bullet strikes the wood, it becomes embedded in it so that both bullet and block move with a common velocity. Let's call it VB, as shown in this diagram. The wire then rises from its original equilibrium position to a height h. And ultimately, what we're trying to do here is to determine the initial velocity of the bullet in terms of m1, m2, and h, the height at which it rises. So we are essentially solving for the way our diagram labels it, V1A. Now, what we have to consider here is that the initial situation is that we have a collision occurring. So here, a collision occurs which is inelastic. Very important here. Inelastic collision. Secondly, so this is in a sense our first step. Okay, this is from A to B. Secondly, here we have this situation here from B to C. This time we have a combination of bullet M1 plus block M2 moving at a common velocity VB, which becomes an initial kinetic energy. In other words, it related to a kinetic energy at the bottom of the swing with, shall we say, y sub b equal to 0. That will become converted to a potential energy where y sub c is equal to h. So we have a kb but a ub that is equal to 0. So kb is not equal to 0. But at point C, UC is not equal to 0. And when I say U, I'm talking, of course, gravity. But KC momentarily becomes 0 at the top of the swing. Now, this situation here from B to C is conservation of energy with no non-conservative forces. So this is scenario number 2. And although they asked us to determine V, what we're going to call VB, what we're really after, and the purpose of using this arrangement of the pendulum is to obtain V1A. That is really the purpose for this device, to obtain the muzzle speed of the bullet. So, armed with this, we now have 2 parts that we work with. Well, let's see. Shall we work backwards? Shall we work with part number 2 first? Why not? In part number 2, we have, well, that might make things a little bit difficult. We'll start with 1. I'm sure that you prefer that. That is the collision event. In the collision event, we have M1, the bullet, moving with V1A plus M2, the block, stationary with V2A. Okay, it's not moving. We'll call that event A, where we have the bullet, which is moving, the block, which is stationary, undergoing a collision where now both become embedded, just like the entangled cars, and they now move with a common VB. Okay, so let's reduce this to M1 V1A equals M1 plus M2 VB. The second event is the conservation of energy event. And in this case, we start out with, remember, it's delta K CB, okay, plus delta U G CB equals 0. Now, we start with a kinetic energy, that's at point B, but at the top of the swing, we momentarily come to rest. So Kc equals 0, Kb does not, plus Ug sub c, here we do have potential energy, but at the bottom of the swing where all the energy was kinetic, which is B, we have no potential of energy. And in a sense, that's our zero of energy. So let's see what we have. Minus Kb equals minus UGC. All right, the minuses cancel. Let's not forget where we're going. We are trying ultimately to determine the value of V1A. We get VB in the interim, why not? 1/2 mVB squared. Oh, very important here. What is this M? This M is the combined M. My goodness, we almost forgot to put that there. Equals 1/2, the same M. We might as well write it. Oh, sorry, not the half. No. It's MGH. So it's M1 plus M2. Okay, that's like our combined M. Let's call this M total. Why not? G times Y sub C, which of course they told us is H, which is the height above. Let's see. We have this M1 plus M2 cancels that M1 plus M2. This tells us that VB, let's extend the page a little bit, VB squared equals 2GH. And when we take a square root, we get VB equals the square root of 2GH. Now, let's come back over here where we had used conservation of momentum and substitute square root of 2GH for VB, yielding a value of, let's see if we can write down here, V1A equals M1 plus M2 divided by M1. And instead of writing VB, we write square root of 2GH. And voila, we are finished. We have the speed of the bullet in terms of M1, M2, which would be quantities that would be known, measurable, and H. VB, the interim speed, if desired, is given entirely by the height at which the combination of bullet and block rise to. Okay, last problem. Here we have the following situation. A car of 1,500 kilograms is traveling due east, which we're going to say is the positive I-hat direction. Here is our car, with a velocity of 25 meters per second, of course, in the I-hat direction. A van of 2,500 kilograms is traveling due north at 20 meters per second, so in the positive J-hat direction. Unfortunately, they collide, and as a result, they become entangled, say wheel to wheel are locked. These are, quite frankly, the easiest type of problems to solve for. And as a result, they move at a common velocity, which makes an angle theta along the first quadrant, or in other words, north of east, at some angle. And of course, they ask us to determine that angle and the final velocity. Now, that means we've got two unknowns to solve for. And of course, you know, two unknowns means you have to have two equations that contain the two unknowns. And then in some means, use substitution to eliminate one unknown, and substitute, once you determine that, then substitute it back and get the second unknown. All right, so how do we work through this problem? Well, we have to consider here that we're working in 2 dimensions. And so although this collision is inelastic, conservation of momentum here will be all momentum in the x direction. That will give us one equation. And all momentum in the y direction, which will give us that second equation. And remember, this is an inelastic, okay, which means that, in fact, perfectly inelastic, which means that there will be a common final velocity with 2 components. And let's see, we will have a VFX, which will be given by VF cosine theta, and a VFY, which will be given as VF sine of theta. And so you see, we're going to have both theta and VF to work with. All right, so let's start with conservation momentum in the x direction. M1, V1, initial x. Oh, sorry, this is component, so we don't have to use the vector notation. Plus M2 V2 initial x, which is 0, equals M1 plus M2, remember the entanglement, VFX, which is VF cosine theta. Okay, the second will be conservation of momentum in y. M1 V1 initial y, 0, plus M2 V2 initial y, non-zero, equals M1 plus M2 VF sine theta. Okay, now, how about this? Let's plug in some numbers. VF times the sine of theta, let me first work with the lowest equation I've got here, is equal to M2 V2 initial y divided by M1 plus M2. Now remember, they told us M2 was 2,500 kilograms. V2 initial was 20 meters per second in the j-hat positive direction. M1 plus M2 is 4,000 kilograms. We put everything together and we get 12.5 meters per second for VF sine theta. We do the same for VF cosine theta. We get M1 V1 initial x divided by M1 plus M2. Plug in our numbers. M1's 1,500 kilograms. V1 initials 25 meters per second in the positive i-hat direction. Divide that by 4,000 and we get 9.375 meters per second. What do we do now? Well, easy. How about this? One way we could do several things. We can say VF equals 12.5 meters per second divided by sine theta, if we wish, okay? And then we plug that into here, okay? So VF is 12.5 meters per second sine theta, and here we have cosine theta, and this whole thing equals 9.375 meters per second. And guess what? This is cotangent of theta. Okay? And we can plug that into our calculators, or what might make more sense is to say that VF equals 9.375 meters per second divided by the cosine of theta, then plug that into here, and so we get 9.375 meters per second divided by cosine of theta, and that gets multiplied by sine of theta, and this looks a little bit better, 12.5 meters per second as far as our calculator is concerned, if that's what we wish, because this is the tangent of theta. Regardless, we solve for the angle theta. Let's say we use the inverse tangent, or take an inverse of the first equation, whatever the case is. So inverse tangent of 12.5 meters per second gives us, 12.5 meters per second divided by 9.375 meters per second gives us an angle of 53.1 degrees. Having the angle now, plug that right back into any one of those equations, the VF 9.375 cosine or the first one, and whatever the case is, we get a value of VF which has a magnitude of 15.625 meters per second. And let's just say this is magnitude, which is what we've solved for. Well, this concludes the last part of the problem-solving session for Chapter 9. Until next time.